Good day. This lecture develops the theory of optimal hypothesis tests. Until now, we considered multiple instances of the hypothesis testing problem, and we proposed decision rules based on our intuition. However, we soon realized that even in very simple situations, intuition alone could not really help us. We illustrated that with an example in the previous lecture where both hypotheses prescribe a Gaussian distribution with the same mean and different variances. In that case, we were unable to set the threshold in a satisfactory manner. Other situations where intuition will not typically help us much is when data is multivariate, right, as typically occurs, or even in more general contexts, such as, for example, when data is not Gaussian. And it is critical to realize the impact that our decisions made by the decision rule that we need to design have on the real world. So, for example, the decision may determine whether a patient starts a certain treatment or whether a drug or a vaccine is approved, whether defense missile is launched, and so on. So there may be lives involved and also great sums of money, right? And therefore, we have an ethical responsibility to design a rule that it is as good as possible, right? And if possible, we would like to have an optimal rule. So these observations call for a systematic approach to hypothesis testing. Okay, we need to develop a mathematical theory with solid grounds in order to solve the hypothesis testing problem in a satisfactory fashion. And to that end, we will follow the same procedure as we've been doing in this course. We will first choose a metric that quantifies how good a decision rule is. And in a second step, we will try to find the decision rule that is optimal in terms of that metric. But before we start, I would like to introduce some notation, mainly because it is often used on books. The Q function is defined as the complementary CDF of a standard Gaussian random variable. So this means that Q of x0 is the probability that a standard Gaussian random variable takes a value greater than x0. Okay, so this means that this function returns the area under the PDF and to the right of x0. In contrast, the cumulative distribution function, as we know, is returns the area under the PDF, but to the left of its argument. This means that the CDF plus the Q function will be precisely 1. Okay. In the case that the random variable is not standard normal, so its mean and variance are not 0 and 1 respectively, then one can extend this notation very easily. In particular, the probability that x is less than x0, which as we know is the integral of the PDF up to x0, will be denoted in this way, right? So this would be the CDF of a normal random variable with this mean and this variance, okay? This can be expressed in terms of this CDF here without any subscripts in this way, because remember that we can turn a non-standard Gaussian random variable into a standard Gaussian random variable by subtracting the mean and divided by the standard deviation, right? And therefore, just by virtue of this equation here, this CDF can also be written in terms of the Q function in this way. In MATLAB, you can use the Q function using this function here, QFunc. And for the CDF, you can use norm CDF. In Python, there is also a function for the CDF, but I'm not aware of any function for the Q function. So in that case, you just need to use this CDF and apply this expression here. As planned, let us start by quantifying how good a decision rule is. So to this end, remember our abstract formulation of the hypothesis testing problem. We are given a collection of probability distributions indexed by a parameter vector theta, and our task is to determine whether the theta of the distribution that generated the data is in a set capital theta 0 or in a set capital theta 1. These two sets form a partition of the parameter space capital theta. And in hypothesis testing theory, we typically distinguish two classes of tests. We say that a hypothesis test is simple when these two subsets here contain only one element. They are what we call singletons, right? In that case, we see that both hypotheses totally specify the distribution of the data. When a hypothesis test is not simple, we say that it is composite, okay? So at least one of these two sets contains more than one element. And today we will be focusing on simple hypothesis tests. Next day we will have a look at composite hypothesis tests. So if the hypothesis test is simple, we can adopt this notation. We can define the vector lowercase theta sub 0 to be the only element in this set, and theta lowercase theta 1 to be the only element in this set. This means that this hypothesis test can be equivalently expressed in this way. We just need to test for the value of the parameter, or yet in another form, we can write it in this way. So x has this PDF or has this PDF. Just to simplify our notation to avoid writing a subscript of a subscript, we will be denoting this PDF in this way. Note that we can do this only when the hypothesis test is simple. This notation could not be used in composite hypothesis tests, because we then wouldn't be indicating the distribution of the data, right? Remember our first example from the previous lecture, where both hypotheses prescribe a Gaussian distribution with the same variance, but different means. There we proposed a decision rule where we decide H0 when the sample is less than gamma, and we decide H1 when the sample is greater than or equal to gamma. This decision rule was seen not to be infallible, so we were making errors. This occurred because even under H0 there is a non-zero probability that our observation is greater than gamma. And similarly, under H1, the sample can be less than gamma, right? Correspondingly, we can define two types of errors. We say that an error is of type 1 if the data adheres to the distribution dictated by H0, but we decide H1, right? We say, by the way, we can read this as hypothesis H0 is true, okay? So in the engineering literature, this is typically known as a false alarm. And this term comes from radar, where the typical hypothesis test is H0, there's no aircraft, H1, and there is an aircraft, right? And that's why we call it false alarm, because there's no aircraft, but we decide that there is actually an aircraft. The other type of error would be just the opposite. Hypothesis H1 is true, but we decide hypothesis H0. The corresponding term in engineering would be misdetection, because this occurs when there is an airplane, but we fail to detect it. These two types of errors can be used to define performance metrics for decision rules. In that sense, one natural metric is the probability of committing an error of type 1, which we will call a probability of false alarm using the engineering terminology. This probability is defined as the probability of the event where we decide H1 measured using the distribution dictated by hypothesis H0. Since the tests we are looking at this point are simple, each hypothesis uniquely defines the distribution of the data, and therefore we can use this notation as well. In the example that we are considering, this probability of false alarm is obviously the area under the PDF for H0 to the right of the threshold, because this is the event where we decide H1, right? Of course, this can also be written as the integral from gamma to infinity of the PDF, which remember was under H0. It had a zero mean and variance sigma square. In terms of the Q function and the CDF of a normal distribution, this can be also expressed in this way. The probability of false alarm is typically referred to as the size of a decision rule or test in a statistics context. Or even it can also be called the probability of false positive, and this is because for instance, when we are trying to determine whether a patient has or not a disease, the null hypothesis is that the patient doesn't have the disease, and the alternative hypothesis is that it has it. So therefore, a type 1 error corresponds to a false positive. The other natural metric that we can consider is the probability of committing an error of type 2. In this case, we call it the probability of misdetection. And this will be the probability of deciding H0 measured using the distribution dictated by H1. And therefore, it can be written in this way, in a similar fashion as here. This probability is clearly the area under the PDF for H1 to the left of the threshold, because this is now the event where we decide H0, right? And again, this can be written as the integral of the PDF from minus infinity to gamma. Note that the distribution that we need to use is the one for H1, and therefore the mean in this example is A, and the variance is sigma square. So this probability of misdetection can also be provided in terms of 1 minus the probability of detection, right? So a detection would be when we decide H1 and H1 is true. So we think that there is an aircraft, and there is actually an aircraft there, right? In statistics, we call it a detection. We call it, or the probability of detection is called power of a test, and or alternatively, the probability of true positive for the same reason as we mentioned earlier. And in terms of the Q function and CDF, this is clearly given by this expression. Note that there is a trade-off between the probability of false alarm and the probability of misdetection. So if we increase the threshold, then this area becomes smaller, so that reduces the probability of false alarm, which is good. But that operation will also increase this area, and therefore the probability of misdetection, which is not good, obviously. But this trade-off does not only take place in the toy example that we've been looking at, it holds in general. Whenever we reduce the probability of false alarm, we will be increasing the probability of misdetection. Or equivalently, if we reduce the probability of false alarm, then the probability of detection decreases. Or even in statistical terminology, and reducing the size will result in a decrease in the power. Therefore, we need a means to balance these two performance metrics, and perhaps the most widely used approach is the so-called Neyman-Pearson criterion. So let calligraphic D denote the set of all possible decision rules or tests. Remember that a decision rule is a function of the data that returns either H0 or H1. This criterion says that we need to look for the decision rule that minimizes the probability of misdetection subject to a bound on the probability of false alarm. This alpha is a constant that we call significance level, and we decided beforehand, right? Or it is given to us. Classical values for the significance level are 0.1, 0.01, or 0.001. These values are typically used especially in natural sciences. And since the probability of misdetection equals 1 minus the probability of detection, we can equivalently phrase this program here as maximizing the power subject to a bound on the size. And this is why we refer to the solution of this problem as the most powerful test of size alpha. And note that until now there was a symmetry between hypothesis H0 and H1. It didn't matter what we call H0 and what we call H1. But this criterion entails a loss of that symmetry, right? Because in one case we are maximizing, and in the other case we are constraining the probability of one of these types of error, right? So one could also think of minimizing the probability of false alarm subject to a bound on the probability of misdetection, right? But that would essentially correspond to renaming or naming our hypothesis in the other way. What we called H0, we call it H1, and vice versa, right? So that means that depending on the discipline, there is a standard way of naming the hypothesis. So, for example, if we want to detect a disease, H0 is typically that there's no disease, and H1 that there is a disease. Or if we want to detect enemy aircrafts, then H0 is that there's no aircraft, and H1 is that there is an aircraft. But this is a rather informal way of defining a most powerful test. A more rigorous definition is as follows. We say that rule D is most powerful for size alpha if two conditions hold. First, the rule needs to have size alpha, right? So the probability of deciding H1 when H0 is true needs to be at most alpha. And second, for any other rule whose size is also alpha, the probability of detection needs to be smaller than the probability of detection of the most powerful test, right? So it is this says that it is the most powerful test among all the tests with size alpha, and this says that it actually has size alpha. So let's go for the solution of the optimization problem in the previous slide. Under general assumptions, we have this theorem, which is called the Neyman-Pearson Theorem, and states that for a simple hypothesis test, the most powerful test or decision rule with size alpha is given by this expression. Here we have a function of the data that returns a real number, and this real number is obtained by evaluating the PDFs under both hypotheses on the data. And then this number is compared against a threshold. This threshold must be set so that the resulting probability of false alarm equals the prescribed significance level. And as we can see, the probability of false alarm is the probability that this function exceeds the threshold alpha when H0 is true. This quotient here is referred to as the likelihood ratio, and because remember, a likelihood function is the result of evaluating the PDF on the data. And there is an important terminological distinction here. Remember that we defined a test or decision rule, also known as a detector or a classifier, as a function that takes data as the input and returns either H0 or H1. A test statistic is a function that takes data and returns a real number, okay? So this is a test statistic. And indeed, most of the tests that are used in practice are of this form. They are the result of computing a test statistic and comparing it with a threshold. So there's a very interesting observation here. It is that the most powerful test has always the same test statistic regardless of alpha. So in principle, one could think that the optimal test statistic may be different depending on alpha, right? But this theorem states that it is the same whenever we need to compute a most powerful test. We just need to find the likelihood ratio and then adjust the threshold to attain the desired significance level. So let's go for one example. Here we have a hypothesis test which generalizes our examples, first two examples from the previous lectures. So under both hypotheses, the data is Gaussian with the same variance but different means. And we assume that the mean under the alternative hypothesis is strictly greater than the mean under hypothesis under the null hypothesis. So both or these three quantities are of course given, otherwise the test would not be simple. So let us try to find the most powerful test of size alpha, and the first step is obviously to find the test statistic. So in this case our data is just a single sample, so we can use this notation, and this is therefore the likelihood ratio. We just need to substitute here this PDF with the one indicated by hypothesis H1, right, and this one by the PDF under hypothesis H0, right, and then we evaluate those PDFs at the data. This can be, of course, simplified because these two terms cancel, and we can apply the properties of the exponential to combine them in this way. And now one can just expand these squares to obtain these 6 terms here. Now we can cancel these 2 terms, and therefore the likelihood ratio simplifies to this expression after combining this term and this term. This means that the most powerful test of size alpha is the result of comparing this quantity with a threshold, where the threshold is set so that the probability that this is greater than that threshold under H0 equals alpha. Now that we have obtained the test statistic, the next step is to find the threshold that yields the desired size. So to that end, note that the probability of false alarm for a threshold gamma is the probability that this quantity exceeds the threshold for or measured in accordance with the distribution prescribed by the null hypothesis. And just by using this expression, this can be written in this way. But this is quite cumbersome, so let us try to simplify it a little bit. And to that end, note that this inequality holds if and only if the log of the left-hand side is greater than the log of the right-hand side, right? So this is precisely what we did here. And one can also multiply both sides by -2 sigma square to obtain an equivalent inequality. Note that since this the constant that we are multiplying with is negative, we need to flip the direction of the inequality. It is very important to be extremely cautious with these derivations, because if you mistake the direction of the inequality, instead of making the optimal decision, you will make the opposite decision, right? And therefore your performance will be horrible. So that's why I recommend performing small steps when doing this sort of procedures. So now we can move these 2 terms to the right hand side and divide both sides by -2 mu1 minus mu0. Here we again need to flip the direction of the inequality sign because this quantity is negative. And the reason is that mu1 was assumed to be greater than mu0 in the previous slide. Otherwise, we wouldn't be able to do this step. If we baptize this term as gamma tilde, then this probability of false alarm can be written in terms of the CDF of x0 under hypothesis h0. So this becomes 1 minus the CDF of a Gaussian random variable with mean mu0 and variance sigma square evaluated at gamma tilde. So the procedure now would be to set this probability of false alarm equal to the prescribed significance, and then solve for gamma. Okay, but here we see that there is a one-to-one correspondence between gamma tilde and gamma. So it means that if we are given gamma tilde, we can easily compute gamma. This means that we can solve first for gamma tilde, which would yield this expression here. Note that the CDF is a monotonically increasing function, and therefore it has an inverse. After obtaining this gamma tilde, therefore, we can use this expression to find gamma. So the most powerful test of size alpha is therefore given by this expression, where this is the original test statistic, and this would be the gamma that we obtain in this way. But from this derivation, we saw that this comparison is totally equivalent to this comparison here. We can equivalently compare x0 with gamma tilde, right? The same decision would be made in using both rules, right? And since this one is simpler, we will in general prefer to use this one. This is, in other words, this one is also most powerful, the most powerful test. About the performance, the probability of false alarm is obviously gamma, because we precisely chose the threshold to achieve this goal. And regarding the probability of detection, which is 1 minus the probability of misdetection, this one is, as we know, the probability that this t is greater than gamma under h1, but as we said, it's equivalent to t tilde greater than gamma tilde under h1. So just by the definition of t tilde, this is the probability that x0 is greater than gamma tilde, and again this can be written in terms of the CDF of a Gaussian distribution, but in this case note that the mean must be mu1 in contrast to this case where the mean was mu0. So we have effectively computed our first most powerful test, and we also analyzed its performance. So it's a great step until now. So now let's go for a multivariate hypothesis test. This is something that until now we were unable to do. Consider this example where the null hypothesis states that our data contains only noise, and the alternative asserts that the data contains both signal and noise. As we often do, we will assume that the noise process is zero mean Gaussian with given variance, And in this case, we will also assume that the signal is Gaussian with zero mean and a given variance. So this assumption is common, especially in communications, because information signals are typically designed to have a distribution that resembles the Gaussian distribution. This is because of information theoretical reasons. We can collect now these samples to form these vectors here, which therefore have these distributions under each hypothesis. To obtain the most powerful test of size alpha, as we said earlier, we need to first obtain the test statistic, which as per the Neyman-Pearson theorem is given by the likelihood ratio. So we just substitute here the expressions for the PDFs that result from these assumptions here, and one can now apply the properties of the determinants and the properties of the exponentials to express the test statistic in this way. So one can again obtain the threshold, but as we did before, instead of that, we will first try to simplify the test statistic to arrive at an equivalent but simpler one. So T of x is greater than a threshold gamma if and only if this inequality holds. This is just the result of using this expression and moving this to the right hand side. Now one can take logarithms to arrive at this inequality, and this makes it possible to solve for x, for the square norm of x, right? Note here that this quantity is greater than this quantity, and therefore this number is smaller than this number. Therefore, this difference is negative, and with this minus sign it becomes positive. This means that we don't have to flip the direction of the inequality, okay? We also added here this normalizing coefficient, and this is just because we want to have something meaningful, but I mean, it's totally arbitrary. You can obtain any other equivalent expression is totally fine. So this yields an equivalent test. We just need to compare this power, right? This is the power of the signal x with threshold gamma tilde, which is given by this expression. So again, this we don't need to obtain gamma. It will be enough to obtain gamma tilde. So let us go for the threshold, and the probability of false alarm for a given gamma tilde is clearly given by this expression. Now one can use this definition to write it in this way, and then apply the definition of an Euclidean norm to write the left-hand side in terms of the sum of the squares of the entries of x. So we need to compute this probability, and this may not seem easy at first glance. But whenever we see a summation of independent Gaussian random variables, a neuron in our brain needs to fire and tell us that we need to express this in terms of a chi-square random variable. So remember that chi-square random variable with n degrees of freedom is the sum of the squares of n independent standard normal Gaussian random variables. So therefore we need to write that or this left hand side in this way. So since as we said this they must be standard Gaussian distributions, what we do is to divide them by their standard deviation, right? Note that the mean is 0, so we don't have to subtract it. And note that here we are using sigma w because this is the distribution, this is their standard deviation under h0, right? So if we were under h1, this should be the square root of sigma w square plus the variance of the signal of the signal component. Okay. So here we just multiplied and divided by sigma w square. Now we can move this coefficient to the right hand side, and we have effectively arrived at a sum of the squares of independent standard Gaussian distribution, Gaussian random variables, which is therefore a chi-square random variable with n degrees of freedom, right? And therefore to obtain this probability we can just use the CDF of a chi-square random variable and evaluate it at this point. So we need to now set this equal to alpha and solve for the threshold gamma tilde. So to that end, we again note that we can use the inverse of this CDF because it is monotonically increasing, and now one can just express gamma tilde in this way. So note that again it is not necessary that we go back to gamma, just gamma tilde is enough. As an exercise, I suggest that you try to obtain the probability of detection of this test, and the derivation is similar to this one here. Now let us revisit the performance trade-off that we discussed earlier, but now our perspective will be centered on the test statistic. Note that the test statistic is a function of the data, and the data is a random vector. That implies that the test statistic itself is a random variable, and therefore it has a distribution. Its distribution under each hypothesis will be therefore determined by the distribution of the data under that hypothesis. This means that we can plot both of the PDFs under both hypotheses, right? And in the similar way as we did before. However, earlier in this lecture, we were plotting x0 on the horizontal axis, right? That worked because our observation was scalar valid, right? But if it was, if our data is multivariate, then that approach does not carry over. However, here we are plotting the value of the test statistic on the horizontal axis, and this is always a scalar regardless of whether the data is vector valued, right? Because as we said earlier, a test statistic is a function of the data that returns a real number. So we can always plot something like this. And as we did before, we can analyze the impact of the choice of the threshold on the different performance metrics that we introduced. The probability of false alarm is clearly the area to the right of the threshold and under the PDF of the test statistic for the null hypothesis. Similarly, the probability of misdetection will be this area here, where now the PDF that we need to use is the one dictated by the alternative hypothesis. And the probability of detection will be the rest of the area under the same curve. So we can again see that increasing gamma will reduce the probability of false alarm, but it will increase the probability of misdetection, or equivalently decrease the probability of detection. So the same trade-off as in the toy example remains here. This is sort of a fundamental limit in hypothesis testing. A useful tool to study this performance trade-off is the so-called receiver operating characteristic, abbreviated ROC, whose name comes from the communications literature, but it is used essentially everywhere. To understand what this is all about, note that the probability of detection and false alarm are functions of the threshold, and therefore for each value of the threshold we have a pair of values here. The ROC is the set that collects all those pairs for all values of the threshold. And this can be visualized by plotting these points on the 2D plane, where the probability of false alarm is typically on the horizontal axis and the probability of detection on the vertical axis. So if here we see that if gamma becomes very small, then by the figures on the previous slide, we see that the probability of false alarm will go to 1, and the probability of detection also goes to 1. This means that this point here is obtained when the threshold is very small. Conversely, if the threshold is very large, we see from the figures in the previous slide that both the probability of false alarm and probability of detection will go to 0, and therefore that would correspond to this point. So note that everything should be confined to this square, because the probabilities are always between 0 and 1. An ROC is used not only to visualize all the achievable pairs of PFA and PD, but also to compare detectors. So let us look at a couple of benchmarks here. On the one hand, the ROC of a most powerful test should be above any other ROC, right? This is because it maximizes the probability of detection for each probability of false alarm, right? This is by the very definition of most powerful test. On the other hand, one can think of the so-called oblivious detector, which essentially disregards the data and makes a decision at random. So suppose that T0 is a uniform distribution between 0 and 1 and independent of the observations. In that case, one can form this decision rule by comparing this random variable with a threshold, right? And again, for a small threshold, we will be here, and for a large threshold, we will be here. This is a randomized detector. This is not exactly in the framework that we have discussed so far, where the decisions were deterministic functions of the observations. But these kind of tests are also extensively used. And if we look at the probability of false alarm, we see that it is nothing but the probability that this random variable is greater than gamma. But this is also the probability of detection, right? Because the distribution doesn't depend on the hypothesis. And this means that the probability of false alarm equals the probability of detection, and therefore the ROC is a straight line that goes from the 0, 0 to the 1, 1. And therefore, since this detector ignores the data, we can never, or we should never be below it. If a detector yields a rock that is under this straight line, then it means that it is actually better to decide the opposite to what this detector is telling us. So it is worse than just ignoring the data, right? So everything interesting should happen between these two ROCs. So the ROC helps us visualize this trade-off, but note that it doesn't impose a total order among the decision rules, right? So for example, here this decision rule is better when the probability of false alarm is large, but this one is better when the probability of false alarm is small, right? So therefore, we cannot really say that one of these is better than the other, right? And so to remedy this issue, some people use this performance metric, which is called the area under the curve, which is the integral of the probability of detection as a function of the probability of false alarm. So essentially this would be the area under the curve for detector T2, and this will be the area under the curve for detector T1. This brings us to an end. Our starting point today was the abstract formulation of the hypothesis testing problem that we introduced in the previous lecture, and we defined a simple hypothesis test as a hypothesis test where these sets are singletons. They contain a single element. A composite hypothesis test is a hypothesis test that is not simple. And we define two classes of errors. And type 1 error or false alarm occurs when we decide H1 but H0 is true, whereas a type 2 error occurs when we decide H0 but H1 is true. We quantified the performance of decision rules using the probabilities of these errors, and we observed that there was a trade-off between these quantities. That took us to introduce the Neyman-Pearson criterion that tells us that we need to maximize the probability of detection, also known as power, subject to a bound on the probability of false alarm, also known as size. And then we presented the Neyman-Pearson Theorem, which provides precisely that the test that is optimum according to that criterion. And note that it only applies for simple hypothesis tests. Then we looked at some examples and introduced the notion of ROC, which is used to visualize all achievable pairs of probability of false alarm and probability of detection, as well as to compare detectors. We also talked about the area under the curve as a way to establish a total order in the class of decision rules. What is coming up is to look at the case where the hypothesis test is composite, so there is some uncertainty or some ambiguity in what is the distribution of the data under at least one of the hypotheses. And we will also be looking at the case where there is some prior knowledge on what hypothesis holds true. So we will continue in the next lecture. Thank you very much for your attention.